This is the slide that I was thinking about earlier. But what about that 17 peak? Where does that come from? Should ask you if you guys have any thoughts. What could possibly give you a 17 peak when you're dealing with methane? Yeah? Well, actually, that's not unreasonable, but if the mass spec is done properly, the high vacuum should prevent that. What she said, for the rest of you who may not have heard, is what if a hydrogen atom radical attacked the methane molecule and therefore you really had CH5? There's a possibility there. But again, if it's done properly under high vacuum, then bimolecular processes should be limited. So I'm looking for a different reason. Any ideas? Any other ideas? How are at? Yeah? There you go. That's the one I was looking for. She said when the carbon itself doesn't equal 12 because it's an isotope, right? Remember how atoms are found in nature. You don't find pure isotopes. You find carbon as C12, C13, and a wee little bit of C14. Not so much of that, but C13 is the main one, right? And the relative abundance in nature is that for every, if you had 100 carbon atoms, one of them would be C13. Now there's another source too, it's a little less abundant, but the hydrogen itself, correct? Because hydrogen in nature is hydrogen proton, right? But also deuteron and also a wee little bit of tritium. But the deuterium that's present is enough to also add 1 to the molecular weight and yield 17. So yeah, good. It does come from isotopes. So it's primarily due to C13H4, right? Not C13 as in you got 13 Cs, but C13 as in the isotope C13. And there's this fancy formula that you can use to figure out the relative abundance of what we call an M+1 peak. Okay? And this becomes a very good way of discerning molecular formulas as well. Because for a given molecular formula, if you're looking at a molecule that has not been manipulated so that it would be enriched in one particular isotope, then you can always predict the relative abundance of the M+1 peak and look at the spectrum and see how close you are. In fact, you don't really have to calculate this stuff. There are tables out there, by out there I mean on the web, where this has already been done for you up to molecular weights of like 300. So you can find the relative abundance of an M+1 peak for just about any molecular formula by looking for it online. Also, there's probably an app for that. Honestly, I haven't looked for it, but I suspect somebody's done it. There are a lot of oddball apps out there today. All right, and that's about all I want to say about that, really. Questions or anything? Okay. So, what, that do too fast? Well, do you need to read more?
No.
Photographic memory? Ah, good. Okay. So, yeah, in this particular case, it's basically a 1% probability for having C13. And so if you go back and look at that data, then you would find that that's approximately the relative height of the M+1 peak for methane. And it does work in an additive way, right? Because if you have 5 carbons, then there's a 1% probability of any one of the 5 carbons being replaced by C13. So that gives you a relative peak now of 5.5% for the presence of C13. So see how that kind of works? I'm not likely to ask you to do this kind of stuff, but just realize how it does work. You're dealing with probability here. Probabilities are not always easy. to play with. But as molecules incorporate more and more carbon, then it's each carbon has a 1% probability of being C13. Okay? And so that's how you can use the M+1 peak, especially in low-res mass spec, to realize how many or what a likely molecular formula is for a particular compound. And I suspect that's about all there really is important on that slide. I should delay a second or two to give you guys a chance to write it down. Even though they'll be on the web later, I notice nobody's looking, so I'll probably stop doing that soon. I have other plans. So I take a short break and play the music in my mind. Hey, that's a good tune. Oh, now Bugs Bunny just interfered. Overture, curtains, lights, this is it. Not never mind. All right, on. Here's a table out of the book that you guys can look at to see what other important what other important isotopes there are. And I'll point out a couple because they matter the most when looking at mass spectrometry. Mass spectra, I should say. The two that matter the most are down here. I circled the wrong two. Here they are. Chlorine and bromine. Right? Hope you guys remember this, perhaps from Gen Chem. It's not the kind of thing that you look at very often, though. But in the case of those two halogens, they each have a very important isotope that really upsets their atomic mass as far as the average found in nature, right? So when you think back to Gen Chem and you did exercises where you took a molecular formula and you tried to figure out a molecular weight, you always use for chlorine 35.5, right? There's no way a pure isotope would ever weigh a half, correct? I hope you guys all realize that. But the 35.5 comes from the average of the two important isotopes, chlorine 35 and chlorine 37. They appear in nature in a 3-to-1 ratio and therefore average out to 35.5. So one's 35, the other one's 37, 3 parts of one part the other yields 35.5. Bromine's the other one that's important. Now notice there's the last column is relative abundance. Notice that that's almost 1. So bromine's the same way. In nature it's 79-81, pretty much a 50-50 ratio. That leads to an average atomic weight of 80. So that's the number you always used in Gen Chem when calculating molecular formulas that might have contained bromine. But this leads to very interesting mass spectra that allow you to know at a glance whether chlorine or bromine is present. Some of these others matter too. Notice that silicone has some interesting abundances. Oxygen's also an M+2 isotope because oxygen 18 is more abundant than oxygen 17 as far as isotopes go. But the bromine and the chlorine are the ones I want to focus on.